Hey guys, welcome back to Proof and Principles. In this session, we will be learning about how to prove Leibniz theorem in a very systematic way. Very first, let us revise what actually Leibniz theorem is. As we discussed in our last session, when we have y as product of two functions, that is u times v, where u and v are differentiable functions, so the general form for finding out the nth order derivative is given by summation r equals to 0 to n choose r, u r, v n minus r, or we can say rth order derivative of u and n minus rth order derivative of v. But in short, you can say it as u power r, v power n minus r. Alright, this is a binomial coefficient whose value is n factorial upon r factorial times n minus r factorial. Now to prove Leibniz theorem, we use principle of mathematical induction, PMI. Okay, so step number 1, where we verify for n is equals to 1. So we will be using one standard result, which is d by dx of uv. This is first order derivative for the function uv. It is given by u prime v plus uv prime. Alright. So this is, I'll write it as by product rule. Okay. So we will prove this result by using Leibniz theorem as well. So by applying Leibniz theorem, we can solve it. So Leibniz theorem is summation r equals to 0 to n choose r, u power r, v power n minus r. From here we can say we are finding the first order derivative, that is where n is equals to 1. So value of n is 1 and r is 0 to n. So r is 0 to r equals to 1. So r is 0 to 1. Alright. Now as we know all the values, we can directly substitute them. So we will be getting 1 choose 0, u0, v1 plus 1 choose 1, u1, v0. By using formula of binomial coefficient, you will get the values as 1 and 1 for both of them. This is 0th order derivative of u, which is u itself, and this is first order derivative of v, which is v prime. Similarly, this becomes u prime v. So you got the same result as that of product rule. Hence, Leibniz theorem is true for n equals to 1. Alright, so this was our step number 1. Now step number 2 says that assume it is true for n equals to m. So substituting value of n as m, we can directly write dm uv is equals to summation r 0 to m choose r, u power r, v power m minus r, and we are assuming that it is true for n equals to m. So step number 3 says differentiate both sides. So this we got from step number 2, but we need to prove for n equals to m plus 1. Okay, this is according to mathematical induction. For n equals to m plus 1, we can say it is dm plus 1, and dm plus 1 can be written as d times dm. Okay, since base is same, so power can be added. You will be getting dm plus 1, and value of dm we already know from this. So this is value of dm. We can directly write dm plus 1 for the function uv is given as d times dm, which is summation r equals to 0 to m choose r, u power r, v power m minus r. Now since this part is constant, we can take this out. You will be getting summation r 0 to m choose r, and d of u power r, v power m minus r. This is all about step number 3. Step number 4 says apply product rule. So as we got this from step number 3, we will be using product rule on this particular part. So I'll write it down separately. We need to find d for u r, v m minus r. Okay. By using product rule, which is d by dx for the function ab, which is given by a prime b plus ab prime. So by using this, we can directly write this as u r plus 1 Vm minus r plus u power r v power m minus r plus 1. Now substitute this particular part in the summation. We will be getting summation r equals to 0 to m. M choose r. Take the first part, which is u power r plus 1 v power m minus r, plus summation r equals to 0 to m. M choose r. Now take the second part, which is u power r v power m minus r plus 1. Step number 5 says expand both summations. As we got this from step number 4, so we have to separate the summations first. This is first summation and this is second part. Now we have to take r 0 to m. So take all the possible values of r here. That is, initially we have to take r is equals to 0 and substitute in the first part. So we'll get u prime vm. Okay. For r is equals to 1, it is m u double prime vm minus 1. For r is equals to 2, we'll get m choose 2 u triple prime vm minus 2. So on till r is equals to m, that is last term we can say, we will be getting u m plus 1 v. Okay. So this is from the first part that we got. Now from the second part, again consider r is equals to 0. When we substitute r is equals to 0 in this, we will get uv m plus 1. Okay, uv power n plus 1. For r is equals to 1, it is m u prime vm. Similarly, for r equals to 2, it is m choose 2 u double prime vm minus 1. For r is equals to 3, we get m choose 3 u triple prime vm minus 2. So on till r is equals to m, we get um v prime. Alright, so these are all the results that we have obtained from first and second summations. Now we have to sum the first summation separately and second summation separately. From first summation, we get u prime vm plus, this was for r equals to 0, alright. Then for r equals to 1, we have to just sum them. Then m u double prime vm minus 1 plus m choose 2 u triple prime vm minus 2, so on till um plus 1 v. So this was from first summation. Now similarly, from second summation, uv m plus 1 m times u prime vm plus m choose 2 u double prime vm minus 1 plus m choose 3 u triple prime vm minus 2, so on till um v prime. Step number 6 says common terms. Like the result that we obtained, we have to just take common terms. So as in the first summation, we have u prime vm. So this is also there in the second summation, which is here u prime vm, alright, but their coefficients are different. Here the coefficient is 1 and here the coefficient is m. Similarly, u double prime vm minus 1, here coefficient is m and here coefficient is m choose 2. These we have to take the common terms and we have to solve them separately. In step number 6, terms involving u prime vm from first summation and second summation. So from first sum we get 1 as our coefficient and u prime vm. Similarly, from second sum we get m as our coefficient times u prime vm. Okay, so 1 is the coefficient from first sum and m is the coefficient from second sum. So from this we can say total coefficient can be written as 1 plus m. If you write this in binomial form, 1 can be written as m choose 0 and m can be written as m choose 1. This 1 plus m can be written as m choose 0 plus m choose 1. This is the result that we obtained from terms involving u prime vm. Next term, which is u double prime v m minus 1. From again first sum, we get u double prime vm minus 1. So from first sum we get m, and from second sum we get m choose 2. So it is m times u double prime vm minus 1, and from second sum it is m choose 2 times u double prime vm minus 1. So again total coefficient is written as m plus m choose 2, and again m can be written as m choose 1. So we can write this as m choose 1 plus m choose 2. This is the total coefficient. Now the next common term is u triple prime vm minus 2. Okay. So from the first sum we get m choose 2 u triple prime vm minus 2. If you notice here, from second sum we get m choose 3 u triple prime vm minus 2. Alright, again we get total coefficient as m choose 2 plus m choose 3. Common pattern from here, that is every middle term gets m choose r plus m choose r minus 1. If you notice carefully, this is m choose r and this is m choose r minus 1. This is m choose r, this is m choose r minus 1. Similarly here, so this is the common pattern that we have noticed. So this happens because same derivative term appears once in first summation and once in second summation. Okay, now step number 7, which says use Pascal's identity. We know that m choose r plus m choose r minus 1 is equals to m plus 1 choose r. This is by identity. If you check the example also, when I have 4 choose 0 plus 4 choose 1, so this will be equals to 5 choose 1. So therefore we can say every coefficient changes into m plus 1 choose r. Hence we can write dm plus 1 for the function uv is given by summation r equals to 0 to m plus 1 choose r u power r v power m plus 1 minus r. Alright, so if you notice that this is exactly the theorem for n equals to m plus 1. Hence we have proved the Leibnitz theorem. We have shown that Leibnitz theorem is true for n equals to 1. If true for n equals to m, then it is true for n equals to m plus 1 as well. So therefore, by principle of mathematical induction, Leibniz theorem is true for every positive integer n. Alright. Now, summary for all the steps that we did to prove Leibniz theorem. This is the first step where we verified that it is true for n equals to 1. This is step number 2 where we assumed that it is true for n equals to m as well. Step 3, which is differentiating both sides, where we did dm plus 1 is equals to d times dm. Then this is step number 4 where we applied product rule. Step number 5, expand both summations. We had first summation and second summation. Step number 6, common terms, take out the common terms. And step number 7, that is use Pascal's identity, m choose r plus m choose r minus 1 is equals to m plus 1 choose r. Subscribe for more such engineering oriented videos. Thank you.